morning. My talk today is in a certain sense an experiment showing up at a numerical weather prediction meeting, but I hope it'll be a very fruitful experiment because what I'd like to talk about is the use of data assimilation techniques. Data assimilation to me is a method, and I think most of you in the room know this. I am going to say a lot of things about data assimilation that you've heard. I'm going to say some things about the use of the general method that maybe you haven't heard, and I'll illustrate it with examples from laboratory experiments, which is a realm in which one can often do a great deal more than we can with the ocean atmosphere, and as we learned this morning, with the human system as well. It's very difficult to do experiments there to test underlying properties of the theory. Okay, that's great. Thank you very much. So I'm going to start out by talking a little bit about the formulation of data assimilation from a physicist's point of view. It's not very different from that of a meteorologist or oceanographer's point of view, but it does emphasize what it is that we actually must do. Turns out that we must do very high dimensional integrals. Whether we do them by variational methods, Monte Carlo methods, or other methods is entirely up to you. But I want to show you how they can be used in action on small but complicated systems and where one goes in using them in more complicated systems. So that's what I've just said. I am going to discuss today two kinds of uses of data assimilation, but I also was able to construct a relatively long list of applications, and those applications are the following. Now, this was not a difficult list to compile. I simply went around and read 3 or 4 papers in each of these fields. I am in no way an expert in the details, the laboratory experiments, or the interpretation of the experiments in every one of the fields. But it was clear that the techniques, in one way or another, were aspects of what we call data assimilation. I'm going to talk about biophysical modeling of neurons and functional networks. I have a very specific network in mind, and I have data from experiments that, using data assimilation methods, we designed the experiments. The experiments were carried out, and we analyzed the experiments and showed that we could, from these experiments, determine the detailed electrophysiological character of individual neurons. And the reason for that is that's the simplest system to begin with. The ability to characterize large circuits of neurons is more difficult, but it has to do as much with knowing measurement functions in, I'm going to switch back and forth with language here, in the standard notation of numerical weather prediction. These are the measurement functions, h of x. Those are actually very difficult in biological examples, but not impossible. I'm also going to talk about the idea of neuromorphic engineering, in which one takes the information that one learns from these experiments on the detailed electrophysiological properties of neurons, or more important, actually, on circuits of neurons that have functions. Individual neurons don't perform functions. They have to be in networks. Transfer that information to VLSI silicon chips, and then use the methods to perform engineering applications of the functions. For example, I will talk about the Birdsong System. I will not talk about it in great detail, but the Birdsong System is a method by which a very large number of species of birds, about 6,000 of them, communicate with each other and functionally use vocalization to achieve the attraction of mates, the rejection of predators, and communication when flying in flocks to go from one place to another. I'm not going to talk about all of the other things. You can see it covers an enormous spectrum of subjects. So this is what a neuron, this is what a neurobiologist looks at when studying the examples that I have in mind. So let's see, here we go. This is a pretty simplified version of a neuron. They're not spherical, but for these purposes, it doesn't much matter because they are described by electrostatic fields whose wavelength is much, much larger than them. And so the actual detailed construction at first order doesn't matter too much. They are described by a set of equations that were developed by Hodgkin and Huxley in the 1950s, little interrupted in the 1940s, and in the 1930s at Cambridge in England, and it was Hodgkin Huxley plus a whole collection of other people. This top equation is current conservation, because these neurons are little nonlinear oscillators that respond to current that is injected into them either directly by the experimenter or received from other neurons. That's the forcing function. That's the equivalent of the winds at the surface of the ocean, if you like. The neuron responds through this equation by giving a voltage, which is the voltage across the cell membrane, which is indicated here. The cell is order of a micron. The cell membrane is order of 10 nanometers, just to give you a scale here. What one can do in experiments on individual neurons is to inject a current. I will show you explicitly some of the currents that are used, and measure the response voltage. And from that, in this relatively simple model, abstracted from what Hodgkin and Huxley did in the 1950s, we have 4 state variables. One is the voltage. The other 3 are the probability or the permeability of the cell membrane to sodium ions, potassium ions, and in this really simple model, a simple characterization of the cell membrane as a capacitor. The question is, can we, by measuring one quantity, these numbers D and L will become clear when I go along a little bit further, by measuring one quantity as a function of time, namely the voltage, can we determine the other 3 quantities, M, H, and N, which tell us how the proteins that let sodium and potassium into the cell vary in their permeability to those ions as a function of voltage. Furthermore, in characterizing the cell, we have on the order of 20 unknown parameters, and we have to measure those as well. I will show you how we do it, and I will show you the results. And how do we test the model that we have constructed for the input-output properties of this neuron? We measure the time series of one quantity, the voltage. We infer, using the model as a nonlinear filter, the time series of the other 3 unobserved state variables, all the parameters. And after we have observed for a certain amount of time, which is order 1 second in most of these examples, 1.5 seconds maybe, we check the model by asking whether or not, when a new current is presented to the neuron, can we predict how the neuron responds? If we can, then we call this neuron verified. Now, not all neurons that perform the same function are identical. There's a distribution, in particular, of the parameters that allow the neuron to perform its function. But once the neuron is verified, we can put it into a network in which it is connected to other neurons. And then we have the task of determining the strength of the connections and the time constants associated with those connections. Those are the synaptic connections among neurons. And we can build a circuit. Building the circuit is another data assimilation problem because you have to determine new parameters, the strengths of the connections, and the time constants associated with the connections. And once you do that, you can build a functional circuit. That's the goal of applying these methods in a neurobiological context. Notice I didn't say anything about mammalian brains. They're too complicated. I will say something about neurons in mammals, but not about the brains themselves. neuroscience is not solely about your brain. It's about how neural circuits work. All right, this is the challenge. Using the laboratory experiments, build these biophysically based neurons, design the experiments using data assimilation methods, basically what you call OSSEs and we call twin experiments. All right? And those are used to design the experiments that you can carry out in the laboratory. So we have to create a model of the functional network of interest. That means you have to know something about the underlying biophysics, but you don't have to know very much. You're going to determine it. Secondly, use the model itself, design these experiments using twin experiments, or I don't know, I can't remember how you pronounce OSSE, Aussies or something like that. But that sounds like you're doing it near New Zealand. Then you use the model along with the data, which are voltages across membranes, and you determine the unknown parameters and the unobserved state variables. You have to determine those as well, and then you can validate the model via prediction. That's the goal. That is not the only view of how to do neuroscience. Another widely spread view is that you guess what the circuit is. You build the circuit in either software or possibly even in a neuromorphic chip, and then you ask whether or not the circuit behaves the way that you expect it to, and then you call that success. I'm personally not very interested in that. Some of you may be, and I am here to wish you good luck. All right. Why would we want to know the detailed electrophysiological properties of individual neurons? Here's an example that we are ourselves involved in that must be multiplied many, many times over various laboratories. There is a set of neurons in mice. The neurons are what we call wild type, normal, healthy neurons. And the other set of neurons have been genetically modified so that the mice exhibit aspects of Alzheimer's disease. Using the methods that I will describe, and we are able to determine the difference in the sodium, potassium, and calcium activity of the individual neurons to determine the difference between the Alzheimer's mice and the normal mice. That difference in the hands of a molecular biologist or a pharmacologist can lead to interventions and treatment for Alzheimer's disease. We do not have to model the entire brain of a mouse or human in order to achieve that kind of goal. Let me move on. Here's a system that I primarily look at. Dan Meliza and Elaine Nogaret will talk about that on Thursday. Wednesday, I think, whatever it is, in a couple days. And it's not a trivial system. It is the Avian Brain with an emphasis on the part that gives rise to production of song. There is a center that connects to the auditory feedback, listens to the world around it, in particular other birds. This center is a command center that generates commands down through a little network to the muscles that are associated with breathing and the other muscles that are associated with the vibration of the equivalent of our larynx, and that produces the song itself. Most of the work that has been done in what I'm describing has been on this nucleus of neurons. It's a few times 10 to the fourth neurons, which itself is a major challenge. All right, here's what is actually done. It's done at the Neurobiological Laboratory of Dan Margolius at the University of Chicago. We isolate neurons from the avian song system. On each neuron, we have a collection, a library of different applied currents for different ways of forcing the system. We can learn from those forcings, and we can validate the neuron as it responds to other forcings. We observe only the membrane voltage. Just for completeness, we sample at about 50 kilohertz. That may be oversampling, but there's no problem with that. And we use all of this to do what I described, estimate the unknown parameters and so forth. Here's an example of data. At the top panel, we have the current in nanoamps as a function of time. This is about 2 seconds of time, with delta t here being 0.02 milliseconds. This is the voltage response of the neuron. And from that, we want to estimate the order 10 state variables, order 50 parameters of a model of Hodgkin-Huxley type, which has biophysical interpretation of the neuron itself. That's the challenge. Okay, now I'm going to talk about data assimilation. Essentially, everybody in the room will understand everything I've said. You've heard it before. I'm going to put it into a context which casts the problem to be carried out as a statistical physics problem and tells you how we do it. Okay, so we're dealing with noisy measurements. There's measurement error. We're dealing with models that are uncertain. There's model error. And we have to represent that in some sense. And I'll show you how we do it. It is not different. Okay? And statistical data assimilation is a recognition that what we're really dealing with is the probability distributions of the state of the system conditioned on the measurements. What does that picture mean? Well, there's a window from some initial time to some final time during which we take the measurements. We start at the initial time with an initial probability distribution. This is often called the prior. In physics, it's called the initial condition. We then move the system from time 0 to time 1, at which point we make an observation, which gives us a modification of the probability distribution. We then move the system from time 1 to time 2, at which point we make a modification that tells us the effect of the measurement. And we continue that cycle until we get to the end of the measurement window. And the overall probability, conditional probability, for all of those states of the system, which I call X, given all of those measurements, however many they are, is simply this product of information transfer at the measurements, the dynamics of the system, and I write that as e to the minus A0x. A0 is the log probability of the conditional probability distribution. And what can you do with the probability distribution? You can ask for expected values of interesting functions on the system. So if you have a function on the state of the system, that includes the parameters, you can ask for the expected value of that function with this probability weight and normalize like this. That's the problem, to do the integral. First, let me tell you a little bit more about what I call the action. If this were really a statistical physics problem, that thing called H0 would be the Hamiltonian over KT, but the fluctuations here are not thermal. They have to do with the measurement errors and the model errors. Here's a little bit different picture of it. You can think of the source, which is the system that you're measuring in a laboratory or in the field, as a transmitter of information to your model, and the model variables are related to your observations by what are generally here in numerical weather prediction called measurement functions. In nonlinear dynamics, this is called generalized synchronization of the transmitter and receiver. All right, I repeated something here about the neurobiology. Here is the problem, and it says here, everything hinges on the structure of this action in path space. Capital X is not an individual state, but the state of the system as it moves through the measurement window. There are two general methods for doing those integrals that I know of. One was invented by Laplace in 1774. Laplace basically said, find the minima of the action, which give you the largest probability distribution. And that's really easy if the problem's linear. But if the problem is nonlinear, then this action has multiple minima, and you have to find the global minimum. And if you don't, you're not making a good estimation of the integral that you need to do. You're making a wrong estimation of the integral that you're after. So Laplace says, find the stationary points and find those that have positive curvature in relatively high dimensional space. Monte Carlo searches essentially do the same thing with a different methodology. I'm going to talk about the Laplace method. The Laplace method often is called in this room 4D var. All right? There is an advantage of thinking of the whole integral you have to do instead of simply the thing that you have to minimize. And that is, if you think about doing this integral as an expansion around the minimum of A0, you can then ask, what are the corrections to that expansion? How do you know you got the right answer? What if the corrections are larger than the answer that you said dominated the integral? It means you have to do this integral in a different way. Fortunately, for the most common choice of the structure of the action, one can actually prove that those corrections converge in a way that I'll mention. All right, here's the action again. It's information transfer. I would like to note that the information transfer, this means conditional mutual information as defined by Shannon in the 1940s, that the conditional mutual information of the measurement now, with all of the states up till now, also depends upon the measurements up till now. It's common to ignore this, but that can play a very significant role, and ignoring it is mathematically wrong and can be numerically very misleading. This is the dynamics. It's your choice on how you represent the error in the model. And finally, there's the initial condition, which is sitting there to be considered. I'm now going to talk about what I call the standard model in data assimilation. The standard model involves Gaussian errors in the measurements, Gaussian errors in the model, but as long as the model dynamics, here written as little f, is itself nonlinear, this action does not give rise to a Gaussian integral that you need to do, but it's a nonlinear problem. It's not a linear problem. You notice that I've characterized the inverse covariance of the measurement error by something I call Rm for our measurement, and the inverse covariance of the Gaussian error in the model by something I call Rf for the function. I will show you how we use those to answer some of the questions that we want to answer.